On December 25, 2021, a telescope folded like origami launched from French Guiana. 25 years of engineering, 344 steps to unfold in space. 2 years later, the James Webb Space Telescope started sending back images that made cosmologists everywhere quietly panic-revealed, looked nothing like the universe we thought we knew. What exactly did Webb see out there in the dark, and why are some scientists rethinking the story of the cosmos itself? Stay with me as we unravel the images that are shaking. Modern astronomy makes sure to follow and subscribe so you don't miss what comes next. When the first Webb Deep Field image appeared on screens in July 2022, astronomers expected to see what Hubble had always shown them at the edge of space: faint smudges, tiny blobs of light, the cosmic equivalent of baby pictures, small, simple, unformed. Instead, they saw galaxies, hundreds of them, bright, structured, impossibly detailed, and sitting among them, shining with the confidence of something that had no right to exist, was a galaxy catalogue named GLAS-Z13. The Z stands for redshift, a measure of distance and time. The higher the number, the further back you're looking. GLAS-Z13 had a redshift of 13.1. That placed it 330 million years after the Big Bang, when the universe was barely 2% of its current age. Here's the problem: GLAS-Z13 weighs about 1 billion times the mass of our Sunday. It's not a smudge, it's not a blob. It's a fully formed galaxy with structure, with organized star formation, with a brightness that suggests it's been working overtime for longer than it should have existed. The model we'd used for decades, hierarchical formation, painted a clear picture of how galaxies grow. Small clumps of dark matter pull in hydrogen gas. The gas collapses, forms a few stars. Those stars form small dwarf galaxies. Dwarf galaxies collide and merge over billions of years, slowly building up mass and structure. It's a bottom-up process. Patient, incremental, like building a skyscraper one brick at a time. The timeline was supposed to look like this. At 300 million years, you'd have proto-galaxies, chaotic clouds of gas, with maybe a few scattered stars, weighing perhaps 10 million to 50 million solar masses. By 1 billion years, you might see the beginnings of disk structure. By 3 to 5 billion years, spiral arms start appearing. By 7 to 10 billion years, you get something that looks like a mature galaxy: bars, bulges, well-defined rotation. GLAS-Z13 weighs 1 billion solar masses at 300 million years. That's 20 to 100 times heavier than it should be. It's like planting a seed in January, expecting a seedling by March, and walking outside to find a full-grown redwood tree with a trunk 3 meters wide. And GLAS-Z13 wasn't alone. Within the first 6 months of Webb's operation, astronomers catalogued over 10 galaxies at redshifts above 10, each one massive, each one bright, each one structurally more complex than models predicted. A galaxy called CERS 93316 appeared at 250 million years post-Big Bang, already shining with the luminosity of a billion suns. Another JDAS GSZ130 showed clear disk structure at 325 million years, an organized rotating system that shouldn't have had time to settle into such orderly motion. By February 2023, the BBC ran a headline calling it a crisis in cosmology. Scientific American published an article titled "JWST's Massive Galaxies Challenge Standard Cosmology." The numbers weren't just slightly off. They were off by factors of 5 to 10. Hierarchical formation predicted that building a galaxy like GLAS-Z13 would take 3 to 5 billion years, roughly the time it takes for a mountain range to form on Earth, for continents to drift thousands of kilometers, for entire species to evolve and go extinct. Webb found it built in 300 million years, the geological equivalent of a mountain appearing overnight. If you compressed all of cosmic history into a single calendar year, with the Big Bang happening at midnight on January 1st, hierarchical formation said mature galaxies shouldn't appear until late March or early April. Webb found them fully formed by January 8th. The universe, it seems, had no patience for slow construction. Consider this: every model of galaxy formation we've built assumes time is the limiting factor. Stars need time to form. Gas needs time to cool and collapse. Structure needs time to stabilize. We'd calculated those timescales carefully, using physics we trust, gravity, thermodynamics, fluid dynamics. But what if the universe in those first few 100 million years operated under conditions we don't fully understand? What if something about the density, the temperature, the sheer concentration of matter back then allowed processes to run not incrementally but explosively? In March 2024, Scientific American published findings from a deeper survey. The number of massive galaxies in the early universe is 100 times higher than models predicted. Not 10 times, 100 times. If you expected to find one needle in a haystack, you found 100 haystacks made entirely of needles. Quantum magazine interviewed Professor Mike Boylan-Colchin from the University of Texas at Austin in January 2024. He ran the numbers through simulation after simulation, trying to find a scenario where this many massive galaxies could exist this early. His conclusion: the probability of finding this many massive galaxies this early, given our current understanding of structure formation, is less than 1%. Less than 1%. In science, that's not unlikely. We're missing something fundamental. What Glass 13 and its siblings tell us is this: the early universe was not a slow, patient sculptor. It was a forge. A crucible where matter condensed, collapsed, and ignited into galaxies with a speed and efficiency we can't yet explain. The bottom-up model, dark matter seeds gradually pulling in gas, might still be true in broad strokes, but something accelerated the process. Something made the first few 100 million years intensely, violently productive. Was it the density of matter back then packed so tightly that gravitational collapse happened faster? Was it the nature of dark matter itself behaving differently in the extreme conditions of the early universe? Or is there a hidden variable, some physical process we haven't accounted for that acts like a catalyst, speeding up galaxy formation when conditions are just right? We don't know yet. But the existence of these impossible babies forces cosmologists to go back to their models and ask, what did we assume that might be wrong? And here's where it gets stranger. These galaxies aren't just massive, they're bright. Intensely, impossibly bright. Glass 13 isn't sitting quietly in the dark cooling off after a growth spurt. It's blazing with the light of billions of newborn stars all forming at once, faster than physics says they should. The brightness crisis isn't just about size, it's about speed. The universe wasn't just building galaxies too quickly, it was setting them on fire. You walk into a cave you've been told is pitch black. You bring a flashlight expecting to see maybe a few glowing mushrooms, some faint bioluminescence from insects. You click the flashlight on. The entire cavern explodes with light crystals covering every surface, reflecting and amplifying until you're standing in something that looks less like a cave and more like the inside of a chandelier. That's what happened when Webb pointed its instruments at the early universe. The period between 100 and 300 million years after the Big Bang is called cosmic dawn. It's supposed to be dim, sparse. The first stars are just beginning to flicker into existence, scattered across vast distances, separated by oceans of cold hydrogen gas. The universe at this point is like a city after a power outage, 1 or 2 candles per block, barely enough to see by. Webb turned on its detectors and saw a blaze. Galaxies at redshifts of 10, 11, 12, each one shining 10 to 30 times brighter than models predicted. Not just a little brighter, blazing, pouring light into the void with an intensity that suggested something was running at full throttle, burning through fuel faster than anything we'd seen before. Take a galaxy called GNZ 11. Hubble spotted it years ago as the most distant object ever observed, sitting at a redshift of 11, about 400 million years after the Big Bang. When Webb took a closer look in October 2023, the measurements came back shocking. GNZ 11 is forming stars at a rate of 300 solar masses per year. 300 times the mass of our Sun, converted from gas into newborn stars every single year. Our Milky Way. It forms 1 to 2 solar masses per year. On a good year, maybe 3. GNZ 11 is working at 150 times that rate. It's like comparing a wood-burning stove to an industrial furnace. And it's not alone. Across the early universe, Webb found dozens of galaxies in similar states, star formation rates off the charts, brightness levels that didn't match any prediction. One galaxy, MAX 0647 JD, is pumping out 150 solar masses per year. Another spotted in the CES survey hit 200. These numbers aren't outliers. They're becoming the norm. Where is all this light coming from? Stars. Billions of them all being born at once in a frenzy of creation that defies every model of how star formation should work. Star formation has limits. You can't just throw gas together and get infinite stars. There's a feedback loop. When massive stars form, they emit ultraviolet radiation, intense, energetic light that heats up the surrounding gas. Hot gas expands. It becomes harder to compress, harder to collapse into new stars. This is called stellar feedback, and it acts like a thermostat, regulating how fast a galaxy can make stars. Too much star formation. The feedback kicks in, blows the gas away, slows things down. Except in the early universe, the thermostat seems to be broken. These early galaxies are forming stars so fast that they should be blowing themselves apart. The radiation from all those young stars should be heating the gas to the point where it can't collapse anymore. The gas should be escaping, drifting off into intergalactic space, leaving the galaxy with nothing left to work with. But that's not happening. The gas is staying. The stars keep forming. The galaxies keep shining. It's like watching someone sprint a marathon at full speed for the entire 26 miles, without slowing down, without hitting the wall, without their muscles giving out. Physics says it shouldn't be possible. But Webb is watching it happen. There's a term astronomers use for this kind of star formation starburst. It describes galaxies that for some reason go into overdrive, converting gas into stars at rates 10 to 100 times faster than normal. Starbursts are rare. They usually happen when two galaxies collide, compressing their gas and triggering a brief, intense burst of star formation that lasts maybe 10 to 50 million years before running out of fuel. But these early galaxies aren't colliding. They're young, isolated, sitting in a universe that's still mostly empty with plenty of room between them. There's no external trigger, no collision to set off the burst. They're doing this on their own. One hypothesis involves the density of the early universe. At 300 million years post-Big Bang, matter was packed much tighter than it is now. The universe was smaller, about 20 times smaller in each dimension, which means the density was 20 cubed or 8,000 times higher. Gas clouds didn't have to travel far to find each other. Gravity didn't have to pull as hard. Everything was already compressed, already primed to collapse. But even that doesn't fully explain the numbers. 8,000 times denser should make star formation faster, yes, but not 150 times faster. The math still doesn't close. Another idea looks at the composition of the gas. In today's universe, gas clouds contain trace amounts of heavier elements, carbon, oxygen, silicon, left behind by previous generations of stars. These elements act like coolants. They radiate away heat, allowing gas clouds to cool down and collapse more easily. The early universe had almost none of these elements, just hydrogen and helium, which are terrible at cooling. That should make star formation slower, not faster. Unless, and this is where it gets speculative, the very first stars were different. Population 3 stars, as they're called, were hypothetical giants made purely of hydrogen and helium, weighing 100 to 300 times the mass of the Sunday. They'd burn hot, bright, and fast, living only a few million years before exploding as supernovae and scattering the first heavy elements into space. If these stars existed in large numbers, if they lived and died quickly enough, they could have seeded the early universe with just enough carbon and oxygen to kickstart efficient star formation in the next generation. Webb hasn't seen a population 3 star yet, but the evidence is everywhere: the brightness, the speed, the efficiency. Something in those first few 100 million years made the universe extraordinarily good at making stars. And this matters for more than just galaxy formation. This light, the ultraviolet radiation pouring out of these early galaxies, had a job to do. The universe at 300 million years old was still mostly opaque, filled with neutral hydrogen gas that absorbed light like fog. For the universe to become transparent, for light to travel freely across space, that hydrogen had to be ionized, split into protons and electrons by high-energy photons. This process, called reionization, was supposed to take time. Models predicted it would take 500 million to 1 billion years for enough stars to form enough light to be emitted to ionize all the hydrogen in the universe. Webb data from 2024 suggests it happened in 200 to 300 million years. 3 times faster than predicted. Quantum magazine reported in March 2024 that the number of high-energy photons in the early universe was double what models expected. The universe didn't slowly wake up, it flooded itself with light. That's what cosmic dawn looks like through Webb's eyes. Not a gradual brightening, but an explosion. A sudden violent ignition of billions of stars across billions of galaxies all at once, all burning brighter and faster than they should. But brightness alone doesn't tell the whole story. Because when you analyze the light from these galaxies, when you break it down into its component wavelengths, you find something that shouldn't be there yet. Elements. Heavy elements. Carbon, oxygen, nitrogen, even dust. And that raises another question. Where did they come from? Stars make these elements, yes, but stars take time to live, to age, to die, and release their contents back into space. These galaxies are only a few 100 million years old. They shouldn't have had time for even one full stellar life cycle, let alone the 2 or 3 generations needed to build up detectable amounts of heavy elements. Yet there they are glowing in the spectrum. Undeniable proof that the universe's chemistry evolved faster than anyone thought possible. When you look at the spectrum of light from a distant galaxy, you're not just seeing brightness. You're reading a recipe. Every element emits light at specific wavelengths. Carbon at one set, oxygen at another, nitrogen at a third. They create patterns, lines in the spectrum, like a barcode that tells you exactly what's inside that galaxy. Webb pointed its spectrograph at a galaxy called A2744YD4, sitting at a redshift of 8.4, roughly 600 million years after the Big Bang. The spectrum came back, showing strong emission lines from oxygen. Not a trace, not a faint hint. Strong, clear, unmistakable oxygen. Oxygen doesn't come from the Big Bang. The Big Bang made hydrogen and helium with a tiny sprinkle of lithium. That's it. Everything else, every atom heavier than helium, gets made inside stars. Specifically, inside massive stars that fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table until they run out of fuel and explode, scattering their contents across space. So, finding oxygen in a 600 million year old galaxy means stars have already formed, lived, and died in that galaxy. Not just one generation. You need at least 2 or 3 cycles of star birth and death to accumulate enough oxygen to show up clearly in a spectrum. Here's the timeline that should have happened. The first stars, population 3 stars, form around 100 to 200 million years after the Big Bang. They're massive, short-lived, maybe 2 to 5 million years from birth to supernova. They explode, seeding the surrounding space with the first heavy elements. That seeded gas collapses into a second generation of stars, population 2, which live longer, maybe tens of millions of years. And when they die, they add more carbon, more oxygen, more nitrogen to the mix. By the time you get to population 1 stars like our Sun, you have a well-mixed cocktail of elements, enough to form planets, dust, complex chemistry. This process from population 3 to detectable levels of oxygen should take at least 500 million to 1 billion years. A2744YD4 did it in 600 million years. That's tight, but maybe plausible if everything happened fast. But then Webb found galaxies at redshifts of 11, 12, 13, 300 to 400 million years old, showing carbon emission lines, oxygen emission lines, even signatures of dust. Dust is particularly telling. Dust grains are tiny particles a fraction of a micron across made of carbon or silicon compounds. They form when gas cools down and atoms stick together, but you need those atoms to exist first. Dust in the early universe means not only have stars formed and died, but their ejecta has cooled, condensed, and started building complex structures. This is supposed to be a late-stage process, something that happens after billions of years. Webb found dust in galaxies only 300 million years old. In August 2023, a team analyzing the spectrum of a galaxy called MAX 0416Y1 detected a feature called the 2175 angstrom bump. It's a signature absorption pattern caused by carbon dust. The light from the galaxy passes through its own dust, and certain wavelengths get absorbed, creating a dip in the spectrum. The 2175 angstrom bump is the calling card of carbon-based dust grains. This galaxy existed 400 million years after the Big Bang. Dr. Hao Jingyan from the University of Missouri, speaking to Science News in August 2023, said, "We're seeing dust that shouldn't exist yet. It's like finding rust in a brand new car factory. Rust requires iron. Iron requires stars to have fused elements up through the periodic table and then exploded. Carbon dust requires multiple generations of stars to have lived and died, releasing carbon, allowing it to cool and clump. Both require time, more time than 400 million years should allow. So, how did the universe speedrun stellar evolution? One possibility is that the very first stars lived fast and died young. If population 3 stars were as massive as models suggest, 100 to 300 solar masses, they would burn through their fuel in just a few million years. Not tens of millions, not hundreds of millions, just a few million. A star 300 times the mass of the Sun might last only 2 million years before going supernova. If the first stars formed at, say, 150 million years post-Big Bang, and they all died by 155 million years, that's 5 million years to seed the universe, with the first carbon and oxygen. Then the second generation forms at 160 million years, lives for 10 to 20 million years, dies by 180 million years, adding more carbon, more oxygen, more nitrogen. By 200 million years, you have enough heavy elements for dust to form. By 300 million years, you have galaxies glowing with oxygen and carbon emission lines. It's tight. It requires everything to happen on the fastest possible schedule with no delays, no dead time. But it's theoretically possible. Except we haven't found a population 3 star yet. Webb has looked. It's one of the mission's primary goals to find the first stars, the ones made purely of hydrogen and helium, and see what they look like. So far, nothing. No confirmed detection of a pristine element-free star. What Webb has found instead is indirect evidence. Galaxies with chemical compositions that suggest recent enrichment. Spectra showing emission lines from elements that had to come from somewhere. The fingerprints of population 3 stars are everywhere, but the stars themselves remain invisible. Maybe they're just too faint. Population 3 stars would be distant, redshifted, and even though they're massive and bright, they're also short-lived. Webb might be arriving just after they've all died, catching only their aftermath. Or maybe they didn't exist in the way we think. Maybe the first generation of stars wasn't pure hydrogen and helium. Maybe there was some primordial enrichment process we don't understand, something that gave even the earliest stars a trace of heavier elements from the start. Or maybe, and this is more radical, the timeline is wrong. Maybe the Big Bang produced more than just hydrogen and helium. Maybe there's a mechanism we haven't discovered yet that created trace amounts of heavier elements in those first few seconds, giving the universe a head start on chemistry. That last idea is controversial. It would require reworking models of Big Bang nucleosynthesis models that have been tested and refined for decades. But so was the idea of galaxies forming in 300 million years, and Webb made that controversy unavoidable. What's clear is this: the universe's chemistry evolved fast. Faster than the slow, patient timeline we'd imagined. The first few 100 million years weren't a quiet period of gradual enrichment. They were a blitz. Stars formed, burned, exploded, and scattered their contents at a pace we're still trying to comprehend. And this chemistry mattered. Carbon and oxygen aren't just elements on a chart. They're coolants. And they radiate away heat efficiently, allowing gas clouds to collapse and form new stars more easily. Once the universe had even trace amounts of these elements, star formation became easier, more efficient, which means the second generation of stars formed faster than the first. And the third generation formed faster still. A feedback loop, accelerating the whole process. By the time the universe was 600 million years old, roughly the age of A2744YD4, it was already chemically mature. Not as mature as today, where heavy elements make up about 2% of all matter, but mature enough. Enough carbon to form dust, enough oxygen to glow in spectra, enough nitrogen to start building the complex molecules that billions of years later would become the basis for life. The universe didn't wait billions of years to get interesting. It front-loaded its complexity. And nowhere is that complexity more baffling than in the centers of these early galaxies, where Webb has found objects that by all rights shouldn't even fit inside a galaxy that young. Objects so massive, so dense that their very existence is rewriting what we thought we knew about how matter behaves in the early universe. At the heart of almost every large galaxy sits a black hole, not a stellar mass black hole, the kind that forms when a single star dies. A supermassive black hole, millions to billions of times the mass of the Sun sitting at the galactic center, pulling in gas, and stars anchoring the galaxy's rotation. Our Milky Way has one. It's called Sagittarius A star, and it weighs about 4 million solar masses. That's massive, but it's also small compared to the Milky Way itself, which weighs around 1 trillion solar masses. The black hole makes up roughly 0.4% of the galaxy's total mass, a tiny fraction. The tail, not the dog. This ratio holds across most galaxies. Supermassive black holes typically make up about 0.1 to 0.2% of their galaxy's total mass. They're important, they influence star formation, they shape the galaxy's structure, but they're not dominant. They're passengers, not drivers. Then Webb looked at a galaxy called UHZ1. UHZ1 sits at a redshift of 10.1, roughly 470 million years after the Big Bang. It's a small galaxy weighing about 40 million solar masses, roughly the size of a large dwarf galaxy in today's universe. But sitting in its center, glowing in X-rays captured by the Chandra telescope and confirmed by Webb's infrared observations, is a black hole weighing 10 million solar masses. 10 million solar masses. In a galaxy weighing 40 million solar masses, that's 25% of the galaxy's total mass. Not 0.1%, 25%. The tail is wagging the dog. And the tail is so heavy, it's a wonder the dog can even move. UHZ1 isn't an outlier. Webb has found dozens of early galaxies with similarly overmassive black holes. In some cases, the black hole weighs as much as the entire stellar population of the galaxy. In one extreme case, a quasar designated J0313-1806, observed at a redshift of 7.6, about 670 million years after the Big Bang. The central black hole weighs 1.6 billion solar masses. 1.6 billion. At 670 million years, there's a speed limit to how fast black holes can grow. It's called the Eddington limit, named after the astrophysicist Arthur Eddington. When a black hole pulls in matter, that matter heats up, emits radiation, and that radiation pushes back against the infalling material. If the black hole tries to eat too fast, the radiation pressure becomes so strong that it blows away the surrounding gas, cutting off the black hole's food supply. The Eddington limit defines the maximum rate at which a black hole can grow without choking itself. For a black hole growing at the Eddington limit, it takes about 50 million years to double in mass. Start with a black hole weighing 10 solar masses, the remnant of a single massive star. 50 million years later, it's 20 solar masses. Another 50 million, it's 40. Another 50, it's 80. You see the problem? To get from 10 solar masses to 1 billion solar masses growing at the Eddington limit without pause takes about 800 million years. The universe at the time of J0313-1806 was 670 million years old. There wasn't enough time. Even if a 10 solar mass black hole formed the instant the first star died, maybe 150 million years after the Big Bang, and grew at maximum speed non-stop for the next 520 million years, it would only reach about 100 million solar masses, not 1.6 billion. The numbers don't work. They're not even close. So astronomers are revisiting an old, somewhat radical idea: direct collapse black holes. Most black holes form from stars. A massive star exhausts its fuel, its core collapses, and you get a black hole weighing 10 to 100 solar masses. This is the standard pathway. But there's another possibility, one that's been theorized since the 1980s, but never confirmed. What if, under the right conditions, a giant cloud of gas, 10,000 to 100,000 solar masses, collapsed directly into a black hole, skipping the star phase entirely? This requires specific conditions. The gas has to be hot enough that it doesn't fragment into smaller clumps and form individual stars. It has to be dense enough that gravity overpowers gas pressure, and it has to collapse fast before anything disrupts it. If all those conditions align, you could get a black hole seed weighing 10,000 to 100,000 solar masses right from the start. That's a huge head start. A 100,000 solar mass black hole growing at the Eddington limit for 500 million years can reach 1 billion solar masses. The math works. The problem is direct collapse should be rare. The conditions are finicky. You need a pristine gas cloud with no heavy elements, because elements like carbon and oxygen help gas cool and fragment, which prevents direct collapse. You need intense ultraviolet radiation from nearby stars to keep the gas hot, but not so much radiation that it blows the gas away. It's a Goldilocks scenario, and Goldilocks scenarios don't happen often, except maybe they did in the early universe. At 300 to 500 million years post-Big Bang, the universe was dense, hot, and full of hydrogen. Galaxies were forming close together, bathed in the ultraviolet light from their neighbors. Gas clouds were massive, fed by steady streams of material flowing in from the cosmic web. The conditions for direct collapse might have been common, not rare. In November 2023, Dr. Priyamvada Natarajan from Yale University, speaking about the UHZ-1 discovery, said, "This is the best evidence yet for direct collapse black holes. We're seeing black holes that are far too massive to have grown from stellar remnants. The only way to explain them is if they started big. But even direct collapse doesn't fully explain the most extreme cases. J0313-1806 at 1.6 billion solar masses would need to start from a seed of at least 10 million solar masses and grow at the Eddington limit without interruption, or it would need to grow faster than the Eddington limit, which requires breaking the rules. And there's some evidence that might be happening." In January 2024, ESA News reported findings from a Webb and Chandra collaboration. Several early galaxies show X-ray signatures consistent with super Eddington accretion black holes eating matter faster than the Eddington limit should allow. How? Maybe the gas is falling in from multiple directions, diluting the radiation pressure. Maybe the black hole's spin is amplifying its gravitational pull, pulling in matter more efficiently. Maybe the physics of accretion in the early universe, where gas is denser and hotter, behaves differently than it does today. We don't know yet. But the existence of billion solar mass black holes at 670 million years forces us to consider possibilities we'd previously dismissed. And these black holes aren't just sitting there passively. They're active. They're feeding, glowing, emitting radiation, influencing their host galaxies in ways we're only beginning to understand. In March 2024, NASA News published a survey of over 100 distant galaxies observed by Webb. The finding black holes in early galaxies are growing faster than the galaxies themselves. In today's universe, galaxies and their central black holes grow in lockstep, maintaining that 0.1 to 0.2% ratio. In the early universe, black holes are growing 2 to 5 times faster than their host galaxies. The tail isn't just wagging the dog. The tail is outgrowing the dog. What does this mean? One possibility is that black holes in the early universe played a more active role in shaping their galaxies than they do today. When a supermassive black hole feeds, it doesn't just emit light. It generates winds, streams of high-energy particles and radiation that blast outward, heating the surrounding gas. In today's universe, these winds can shut down star formation, blowing away the gas a galaxy needs to make new stars. But in the early universe, where gas is abundant and constantly replenished by infall from the cosmic web, maybe black hole winds had a different effect. Maybe they compressed gas, triggering star formation rather than suppressing it. Maybe they stirred the gas, mixing in heavy elements, seeding the galaxy with the chemistry it needed to form planets. Or maybe they were purely destructive, and the galaxies we're seeing now are the survivors, the ones that managed to form and grow despite having an overmassive black hole in their core tearing through their gas supply. We don't have answers yet, but the questions are becoming sharper. And as Webb continues to observe, as more data comes in, the picture of the early universe is shifting from slow and orderly to chaotic and extreme. Black holes forming too fast, galaxies feeding them too much, growth rates that shouldn't be possible but clearly are. And strangest of all these chaotic extreme galaxies, these systems that shouldn't exist, that formed too quickly, that host black holes too massive for their age, aren't shapeless blobs. They're not clouds of gas swirling aimlessly. When Webb looks closely, when it resolves their structures, it finds something no one expected: order. Disks, spirals, bars. The architecture of mature galaxies, appearing hundreds of millions of years too early. When you look at a spiral galaxy like the Milky Way, you're looking at the result of billions of years of evolution. The disk is flat, smooth, rotating in an orderly fashion. The spiral arms trace elegant curved sites where gas compresses and new stars form. The central bulge is dense, stable, packed with older stars that have settled into predictable orbits. Everything about it screams mature system. Getting to this point takes time, lots of time. When galaxies first form, they're messy. Gas clouds collide, merge, fragment. Stars form in clumps scattered across the proto-galaxy. There's no disk yet, no spiral structure, just chaos. Over time, through countless interactions, through the gradual smoothing effect of gravity, the system settles down. Random motions average out. Gas that was orbiting at odd angles either falls into the center or gets ejected entirely. What's left forms a rotating disk, flat and stable, where stars can form in an orderly way. This process, dynamical relaxation, takes a few billion years. That's the timeline we've used. And it's worked well for local galaxies. Galaxies we can see in detail, galaxies that have had 13 billion years to evolve. Then Webb looked at galaxies from 2 to 3 billion years after the Big Bang and found them already structured. Disks, spirals, even bars. Bars are particularly telling. A bar is a linear structure of stars cutting through the center of a galaxy perpendicular to the spiral arms. About half of all spiral galaxies today have bars, including the Milky Way. Bars form through a gravitational instability. Once a disk reaches a certain density and stability, stars can organize into a bar-shaped pattern that reinforces itself, funneling gas into the galactic center and influencing star formation. But bars require stability. If the disk is too turbulent, if stars are moving too randomly, bars can't form. They need a calm, ordered environment. And, according to models, bars shouldn't appear until a galaxy is at least 7 to 10 billion years old. In July 2023, Webb observed a galaxy called CERS 2112. Redshift 3, universe age 2 billion years. And sitting right there, clear as day in the Webb image, was a bar. A full, well-defined bar structure stretching across the galaxy's core. Science magazine ran the headline, "Barred galaxies appeared 5 billion years earlier than expected." Dr. Shardha Joji from the University of Texas at Austin, quoted in the article, said, "Bars require a stable disk and time to form. Finding them this early is like seeing a teenager with grey hair." CERS 2112 wasn't alone. Webb found multiple barred galaxies at redshifts between 2 and 4, each one appearing billions of years before Hubble observations suggested bars should exist. Hubble, observing invisible and near-infrared light, could see galaxies at these distances, but the resolution wasn't high enough to detect bars. They were there all along. We just couldn't see them. Now we can. And the implications are clear. Galaxy disks stabilized much faster than we thought. The turbulence, the chaos, the random motions, they settled down, not in 5 to 7 billion years, but in 1 to 2 billion years. Maybe less. And it's not just bars. Webb's surveys have found spiral arms in galaxies at redshifts of 4 to 6, corresponding to the universe at 1 to 1.5 billion years old. Hubble surveys at the same redshifts found spirals in only about 5% of galaxies. Webb 30%. That's not because new galaxies appeared. It's because Webb can see structure that Hubble couldn't. The spirals were always there, but Hubble's resolution blurred them into smooth, featureless disks. Webb's sharper eyes revealed the truth: the early universe was far more organized than we realized. Quanta magazine, reporting in October 2023, summed it up. Early universe was 6 times more organized than we thought. 6 times. Not a little more organized. 6 times. How does this happen? How does a galaxy go from chaotic gas cloud to stable spiral disk in 1 billion years instead of 5? One possibility is that early galaxies experienced fewer mergers than models predicted. Mergers, when two galaxies collide and combine, disrupt structure. They heat up the disk, scatter stars into random orbits, destroy bars and spirals. If the early universe had fewer mergers, galaxies could have settled into stable structures more quickly. But that contradicts hierarchical formation, which says the early universe should be full of mergers. Small galaxies colliding, building up into larger galaxies over time. Fewer mergers would mean less hierarchical formation, which brings us back to the same problem we started with. How are these galaxies so big so soon if they're not merging? Another possibility involves dark matter. Dark matter makes up about 85% of a galaxy's total mass, and it provides the gravitational scaffolding that holds the galaxy together. If dark matter halos in the early universe were smoother, more uniform than we thought, if they didn't have the clumpiness and substructure that simulations predict, then gas falling into those halos would settle more easily, forming stable disks faster. But that's speculative. We don't have direct observations of dark matter structure in the early universe. We infer it from the galaxies we see, and if those galaxies are behaving unexpectedly, maybe our inferences about dark matter are off. A third possibility is simply that dynamical relaxation, the process of smoothing out random motions, happens faster in denser environments. The early universe was denser, galaxies were closer together, interactions were more frequent, but also more gentle. Lots of small perturbations rather than violent crashes. Maybe all those small interactions, rather than disrupting structure, actually help stabilize it, averaging out random motions more quickly. There's some support for this. Computer simulations run in 2024, trying to match Webb observations, found that increasing the frequency of minor interactions, close passes by neighboring galaxies, tidal tugs from the cosmic web could speed up disk formation by a factor of 2 to 3. Not 6, but it's a start. What's becoming clear is this: the early universe didn't wait around. Galaxies didn't spend billions of years stumbling through chaos before finally getting their act together. They organized fast. By the time the universe was 2 billion years old, barely 15% of its current age, many galaxies already looked mature. Stable disks, rotating orderly, spirals and bars forming shaping star formation, guiding the evolution of the galaxy. And all of this speed, this efficiency, this unexpected organization depended on being able to see it. Depended on having a telescope powerful enough to resolve structure across billions of light years, to peer through the fog of the early universe and capture details that just a few years ago were completely invisible. The reason we're rewriting galaxy formation timelines isn't just because galaxies formed faster than we thought. It's because we finally built an instrument capable of seeing them as they really are. The Hubble Space Telescope launched in 1990. For over 3 decades, it was humanity's best eye on the universe, capturing images of distant galaxies, nebulae, star clusters, black holes. It transformed our understanding of cosmology. It measured the expansion rate of the universe. It found dark energy. It peered back to galaxies at redshifts of 8, 9, even 11, pushing the limits of what visible and near-infrared light could reveal. But Hubble had limits. Its mirror was 2.4 meters across, large by the standards of space telescopes, but small compared to ground-based observatories. Its instruments were optimized for visible and ultraviolet light with some near-infrared capability. And crucially, it was designed in the 1980s, built with technology from the 1990s, launched in the early 2000s. By 2020, Hubble was showing its age. Not failing, its instruments still worked, its observations still contributed to science, but it couldn't see what came next. What came next required infrared. Deep infrared. Wavelengths longer than visible light, longer than what Hubble could detect, wavelengths that correspond to light from the most distant, most redshifted objects in the universe. Enter the James Webb Space Telescope. Webb's primary mirror is 6.5 meters across, composed of 18 hexagonal segments, each one coated with a thin layer of gold. Gold reflects infrared light better than aluminum, and infrared is Webb's specialty. The mirror's total collecting area is 6.25 times larger than Hubble's, which means it can gather more light, see fainter objects, resolve finer details. But size isn't everything. What makes Webb revolutionary is where it operates on the electromagnetic spectrum. Light from distant galaxies doesn't reach us in its original form. As the universe expands, the space between us and those galaxies stretches, and the light traveling through that space stretches with it. This is redshift light that started as ultraviolet gets stretched into visible blue. Blue gets stretched into red. Red gets stretched into infrared. The further away the galaxy, the more the light has been stretched, the deeper into the infrared it appears. Hubble could see redshifts up to about 11, corresponding to galaxies about 400 million years after the Big Bang. Beyond that, the light was too redshifted, too deeply infrared for Hubble's instruments to detect. Webb can see from 0.6 to 28 microns in wavelength, deep into the infrared, far beyond what human eyes can perceive, far beyond what Hubble could reach. This allows Webb to see galaxies at redshifts of 13, 14, possibly higher. Galaxies from the first few 100 million years of the universe, galaxies whose light has been traveling for over 13 billion years, stretched and redshifted until it falls perfectly into Webb's range. But detecting infrared light requires extreme cold. Infrared is heat radiation. If Webb's instruments were warm, they'd be glowing in infrared themselves, drowning out the faint signals from distant galaxies. So Webb operates at 40 Kelvin minus 233 degrees Celsius colder than the surface of Pluto. Achieving this requires a sun shield the size of a tennis court made of 5 layers of Kapton film, each one thinner than a human hair. The sun shield sits between Webb and the sun, blocking 99.9999% of the sun's heat and light. On the sun-facing side, temperatures reach 85 degrees Celsius. On the telescope side, 40 Kelvin. The temperature difference across those 5 layers is over 300 degrees. The sun shield isn't just a passive barrier. It's actively designed to radiate heat away into space. Each layer is slightly larger than the one beneath it, creating gaps where infrared radiation can escape without warming the telescope. This design allows Webb to cool itself passively, without the need for active refrigeration, which would add weight, complexity, and failure points. Webb doesn't orbit Earth. It sits at the second Lagrange point L2, a gravitationally stable location about 1.5 million kilometers from Earth, directly opposite the Sunday. At L2, Earth, Sun, and Moon are always in the same direction, allowing the sun shield to block all 3 at once. This keeps Webb cold, dark, and stable, free from the thermal fluctuations and scattered light that would plague a telescope in Earth orbit. But L2 is far, too far for a repair mission. When Hubble's mirror was found to be flawed after launch, astronauts flew up in the space shuttle and installed corrective optics, saving the mission. If Webb had failed, if any of its 344 deployment steps had gone wrong, there would be no rescue, no second chance. $10 billion and 25 years of work would drift silently in space, unfixable. On December 25, 2021, Webb launched on an Ariane 5 rocket from French Guiana. The telescope was folded into a space smaller than the rocket's payload, fairing mirror segments tucked inward, sun shield compressed into a bundle, instruments packed tightly. Over the next month, as Webb traveled toward L2, it began to unfold. The sun shield deployed first, 5 layers, each one unfolding, tensioning, separating from the others. Then the mirror segments, unfolding outward like petals, locking into position. Then the fine adjustments, each of the 18 mirror segments could be tilted and shifted individually, aligning them to nanometer precision, so they acted as a single, perfect mirror. By late January 2022, Webb was fully deployed. The mirror was aligned. The instruments were cold. On July 12, 2022, NASA released the first image, Webb's first deep field, a patch of sky, no larger than a grain of sand held at arm's length, containing thousands of galaxies, some of them over 13 billion, light-years away. Hubble had observed the same region. Its image showed a few hundred galaxies, most of them relatively nearby. Webb's image showed thousands, including galaxies. Hubble had missed entirely galaxies, too faint, too redshifted, too deeply hidden in the infrared for Hubble to detect. But Webb doesn't just take pictures. Its spectrograph NIRSpec, the near-infrared spectrograph, can observe 100 objects simultaneously. Hubble's spectrograph could do one at a time. This 100-fold increase in efficiency allows Webb to survey large numbers of galaxies, quickly measuring their redshifts, analyzing their chemical compositions, determining their star formation rates. NIRSpec works using microshutters, 250,000 tiny doors, each one about the width of a human hair, arranged in a grid. A computer opens and closes specific shutters to let light from selected galaxies pass through while blocking light from everything else. This allows Webb to capture spectra from 100 galaxies in a single observation, something that would have taken Hubble months to accomplish. And then there's gravitational lensing. When light from a distant galaxy passes near a massive object, a galaxy cluster, for instance, the gravity of that object bends the light, magnifying the background galaxy like a lens. Webb uses this cosmic magnification to see galaxies that would otherwise be too faint to detect. The galaxy cluster MAX 0416, for example, acts as a natural telescope, bending and amplifying the light from galaxies behind it. Webb has observed this cluster extensively, finding dozens of ultra-distant galaxies that only became visible thanks to the cluster's lensing effect. Gravitational lensing doesn't just magnify, it also distorts stretching galaxies into arcs and multiple images. By analyzing these distortions, astronomers can map the distribution of dark matter in the lensing cluster and refine their measurements of the background galaxy's distances and properties. Webb has now been operating for over 2 years. In that time, it has observed more than 60,000 hours of targets, contributed to over 600 published scientific papers, discovered over 1,000 galaxies at redshifts above 10 galaxies. Hubble never saw galaxies whose existence was uncertain until Webb confirmed them, and the telescope is performing better than expected. Its fuel reserves needed for small adjustments to maintain its orbit at L2 were estimated to last until 2031. But the launch was so precise and the fuel usage so efficient that Webb now has enough fuel to operate until at least 2035, possibly 2040. What that means is more observations, more deep fields, more spectroscopy, more galaxies, more black holes, more chemical compositions, more data to feed into models that are already struggling to keep up. Because everything Webb has found, the massive galaxies, the bright starbursts, the rapid chemical enrichment, the overmassive black holes, the organized structures, all of it comes down to measurement, to redshift, to being able to look at a faint smudge of light, break it into its component wavelengths, and determine exactly how far away it is, how old it is, what it's made of. And that requires understanding one of the most fundamental tools in astronomy: how to read the stretching of light as a clock, measuring time itself. Light travels at a fixed speed, 300,000 kilometers per second. Nothing in the universe moves faster. When you look at an object in space, you're not seeing it as it is now. You're seeing it as it was when the light left it. The moon is about 1.3 light seconds away. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun is 8 light minutes away. You're seeing it as it was 8 minutes ago. The nearest star beyond the sun, Proxima Centauri, is 4.2 light years away. You're seeing it as it was 4.2 years ago. This time, delay becomes dramatic when you look at distant galaxies. A galaxy 1 billion light-years away shows you what it looked like 1 billion years ago. A galaxy 10 billion light-years away shows you the universe as it was 10 billion years ago. The further you look, the further back in time you see. But there's a complication: the universe is expanding. Space itself is stretching, and as it stretches, the light traveling through it stretches too. When a galaxy emits light, that light has a specific wavelength, the distance between successive crests of the light wave. Ultraviolet light has short wavelengths around 100 to 400 nanometers. Visible light ranges from 400 to 700 nanometers. Infrared light starts at 700 nanometers and extends into microns, thousands of nanometers. As the universe expands, those wavelengths expand too. Ultraviolet light becomes visible. Visible light becomes infrared. Infrared light becomes far infrared, then microwave. The amount of stretching depends on how much the universe has expanded during the light's journey, which depends on how long the light has been traveling, which depends on how far away the galaxy is. This stretching is called redshift because it shifts light toward the red end of the spectrum toward longer wavelengths. Redshift is measured with a simple formula: Z equals the observed wavelength minus the original wavelength divided by the original wavelength. If light that started at 400 nanometers arrives at 800 nanometers, it's been stretched by a factor of 2, giving a redshift of Z equals 1. The relationship between redshift and distance isn't linear because the universe's expansion rate has changed over time, but roughly Z equals 1 corresponds to a look-back time of about 7.7 billion years. Z equals 2 is about 10.3 billion years. Z equals 6 is about 12.7 billion years. Z equals 10 is about 13.2 billion years. Z equals 14 is about 13.5 billion years. The highest confirmed redshift measured by Webb so far is 14.32 from a galaxy called JDES GS-Z140. That places it about 280 million years after the Big Bang, when the universe was just 2% of its current age. But measuring redshift isn't as simple as looking at a galaxy and reading a number off a detector. You need to identify specific features in the light emission or absorption lines from known elements and measure how much those lines have shifted from their original wavelength. Hydrogen, for example, emits light at 121.6 nanometers in the ultraviolet. This is called the Lyman alpha line. If you observe a galaxy and find an emission line at 1,600 nanometers deep in the infrared, you can calculate 1,600 divided by 121.6 equals about 13. So Z equals 13 minus 1, or Z equals 12. That galaxy is showing you light from about 13.3 billion years ago. This process is called spectroscopy. You take the light from a galaxy, pass it through a prism or diffraction grating to spread it into a spectrum and look for lines. Each element has its own set of lines. Oxygen has several in the visible, and near-infrared carbon has lines in the ultraviolet. Nitrogen has lines in the near-infrared. By identifying these lines and measuring their wavelengths, you can determine the galaxy's redshift with high precision. But there's a faster, less precise method: photometry. Instead of spreading light into a full spectrum, you observe the galaxy through several filters, each one letting through only a narrow range of wavelengths. By comparing the brightness of the galaxy in different filters, you can estimate its redshift based on where its light is brightest. Photometry is quick. Webb can measure photometric redshifts for hundreds of galaxies in a single observation, but photometry can be fooled. A dusty nearby galaxy can look similar to a distant, dust-free galaxy if you're only measuring brightness in a few filters. The light gets absorbed and re-emitted by dust in ways that mimic redshift. In the first year of Webb operations, several galaxies were announced, with photometric redshifts of 16, 18, even 20 redshifts, so high they would place them within 100 million years of the Big Bang. Astronomers were excited. These would be the earliest galaxies ever seen, possibly the first generation of star formation, the very dawn of cosmic structure. Then, spectroscopy was done. Follow-up observations with NIRSpec took detailed spectra of these galaxies, and the results came back: Z equals 5, Z equals 6, Z equals 7, not 16, not 20. The photometry had been fooled by dust. This happened repeatedly. By mid-2024, Scientific American reported that about 80% of galaxies with photometric redshifts above 12 turned out upon spectroscopic confirmation to have redshifts between 5 and 8. Still distant, still early, but not record-breaking. The lesson: photometry is useful for surveys, for quickly identifying candidates. But spectroscopy is required for confirmation. And as of February 2024, the confirmed record holder for highest redshift is JADES GSC 14.0 at Z equals 14.32. Nature published the confirmation in May 2024, calling it a galaxy at the edge of time. But redshift isn't just about distance and time. It's also a tool for mapping the structure of the universe. When light from a distant galaxy travels to us, it passes through intergalactic space, and that space isn't empty. It contains clouds of hydrogen gas, remnants of the cosmic web, the large-scale structure that connects galaxies across the universe. Each cloud of hydrogen absorbs light at specific wavelengths corresponding to its own redshift. How far away the cloud is, how much the universe has expanded since the light passed through. This creates a pattern of absorption lines in the galaxy's spectrum, a series of dips called the Lyman alpha forest. Each dip represents a cloud of gas somewhere along the line of sight. By analyzing the Lyman alpha forest, astronomers can map the distribution of gas between us and the distant galaxy, tracing the cosmic web, identifying regions where matter is concentrated, regions where it's sparse. It's like reading a barcode that tells you not just where the galaxy is, but what lies between you and it. Webb uses this technique extensively. By observing bright quasars at high redshifts and analyzing their spectra, Webb maps the structure of the early universe, revealing how matter was distributed, how galaxies formed along filaments of dark matter, how the cosmic web evolved over time. And there's another trick combining redshift measurements from multiple galaxies in the same field of view. If you observe a galaxy cluster, a massive collection of galaxies bound together by gravity, you can measure the redshifts of individual galaxies within the cluster. Most will have similar redshifts because they're all at roughly the same distance, but a few will have very different redshifts. Those are background galaxies much further away whose light is being lensed by the cluster's gravity. By identifying which galaxies belong to the cluster and which are background objects, astronomers can model the cluster's mass distribution, map its dark matter halo, and use the lensing effect to study the background galaxies in detail. This is how Webb studies some of the most distant galaxies. They're too faint to see directly, but gravitational lensing amplifies their light, making them visible. And redshift measurements tell you which galaxies are doing the lensing and which are being lensed. Redshift is fundamentally the ruler and clock of cosmology. It measures distance and time simultaneously. It connects observation to theory, linking what we see in the telescope to models of cosmic expansion, dark energy, the age of the universe. And everything Webb has discovered, every massive galaxy, every bright quasar, every chemical signature, every structural detail depends on knowing the redshift precisely. Which brings us back to the models. The Lambda-CDM model, Lambda for dark energy, CDM for cold dark matter, is the standard framework of cosmology. It describes how the universe expands, how structure forms, how galaxies evolve. For decades, it's worked. Observations matched predictions. The universe made sense. Webb's observations are straining that framework, not breaking it entirely, but revealing cracks, inconsistencies, places where the model doesn't quite fit. And the question now isn't just what did we see, it's what does it mean? What do these discoveries tell us about the universe, about the physics that govern it, about the gaps in our understanding that we didn't know existed? For most of the last 30 years, cosmology felt solved. Not completely, there were open questions, details to refine, but the big picture was clear. The universe began with the Big Bang 13.8 billion years ago. It expanded, cooled, and over time, small fluctuations in density grew into galaxies, clusters, and the cosmic web. Dark matter provided the gravitational scaffolding. Dark energy drove accelerated expansion. Normal matter, stars, gas, planets, us, made up a small fraction of the total, but it was the part we could see and measure. This framework, called Lambda-CDM, fit the data beautifully. Observations of the cosmic microwave background, the afterglow of the Big Bang, matched predictions to astonishing precision. Measurements of galaxy distributions, supernovae, the large-scale structure of the universe, all consistent with Lambda-CDM. Then Webb started observing, and the consistency began to crack. The first crack appeared in the sheer number of massive galaxies in the early universe. Lambda-CDM predicts structure formation happens hierarchically. Small objects form first, merge over time, build up into larger structures. At high redshifts, early times, you should see lots of small galaxies, a few medium galaxies, and almost no large galaxies. The probability of finding a billion solar mass galaxy at redshift 10, according to Lambda-CDM, is extremely low. Less than 1 in a billion cubic megaparsecs. Webb found them everywhere. Not one, not a few, dozens, then hundreds. By March 2024, Scientific American reported that the density of massive galaxies at high redshifts is 10 to 100 times higher than Lambda-CDM predicts. 10 to 100 times. That's not a minor discrepancy, that's a fundamental mismatch between model and reality. What could explain it? One possibility is that dark matter behaves differently in the early universe. Lambda-CDM assumes cold dark matter particles that move slowly clumped together gradually seed structure formation over time. But if dark matter is slightly warmer, if the particles have a bit more kinetic energy, they'd clump faster, form structure earlier, allow galaxies to grow more quickly. This isn't a radical departure from Lambda-CDM, it's a tweak, but tweaks have consequences. Warmer dark matter changes the distribution of small-scale structure, alters the number of dwarf galaxies, affects how galaxy clusters form. You can't just adjust one parameter without affecting everything else. Another possibility is star formation efficiency. Lambda-CDM assumes that when gas collapses into a galaxy, only a small fraction of it, maybe 10 to 20%, actually forms stars. The rest gets blown away by supernovae stellar winds radiation pressure from newborn stars. This is called feedback, and it's a critical part of regulating galaxy growth. But if feedback in the early universe was weaker, if more of the infalling gas stayed in the galaxy and formed stars, then galaxies would grow more massive more quickly. Why would feedback be weaker? Maybe because the gas was denser, harder to blow away. Maybe because the first stars were different, producing less energetic winds. Maybe because the universe's expansion was faster, diluting the feedback before it could have an effect. This explanation fits some of the data. It explains why early galaxies are bright, more gas-forming stars means more luminosity. It explains why their massive, less gas loss to feedback means more mass retained. But it doesn't fully explain the numbers. Even with maximum star formation efficiency, even with zero feedback models struggle to produce the sheer quantity of massive galaxies Webb is finding. A third possibility strikes at the heart of Lambda-CDM initial conditions. The model assumes the universe started with small random fluctuations in density. Quantum fluctuations stretched to cosmic scales during inflation. These fluctuations grew over time, pulled together by gravity forming structure. But what if the fluctuations weren't random? What if some regions started denser than others, giving them a head start on structure formation? This isn't pure speculation. Some modified inflation models predict non-random initial conditions, regions where density fluctuations are stronger, where structure forms earlier. If those models are correct, then pockets of the universe could have formed galaxies faster than the average, creating the high-density regions Webb is observing. But this opens a can of worms. If initial conditions varied significantly, then the universe's large-scale structure, the distribution of galaxies across billions of light-years, should show corresponding variations. And so far, observations of the cosmic microwave background show the opposite. Initial conditions were remarkably uniform. Any variations were tiny, less than 1 part in 100,000. So we're left with a puzzle. Lambda-CDM, based on uniform initial conditions, cold, dark matter, and standard feedback, predicts a universe where massive galaxies are rare at high redshifts. Webb observes a universe where they're common. Something has to give, and the problem compounds when you add in black holes. Lambda-CDM has no good explanation for billion solar mass black holes at 600 million years. Direct collapse? The idea that massive gas clouds can collapse straight into black holes helps, but it requires conditions that should be rare. Webb is finding these black holes everywhere. Either the conditions for direct collapse were far more common than we thought, or black holes grew faster than the Eddington limit, or black holes formed through some mechanism we haven't considered yet. Then there's the Hubble tension. This is a separate problem, but it's related. The Hubble constant 0 describes how fast the universe is expanding. Measure it one way using the cosmic microwave background, and you get 67.4 kilometers per second per megaparsec. Measure it another way using supernovae and variable stars, and you get 73. That's an 8% difference, and it's not going away. For years, astronomers hoped better measurements would resolve the tension, that one method or the other would turn out to be wrong. Webb has now measured the distance to variable stars with higher precision than Hubble. The result, 73. The tension remains. What does this mean? One possibility is that the universe's expansion rate has changed over time in ways Lambda-CDM doesn't account for. Maybe dark energy was stronger in the past, accelerating expansion more than expected. Maybe there's an unknown component, early dark energy, that influenced the universe's evolution during the first few billion years. Another possibility is that the universe isn't expanding uniformly. Maybe our local region, the patch of space within a few billion light years of us, is expanding faster or slower than the cosmic average, creating a measurement bias. Or maybe Lambda-CDM is simply incomplete. Maybe there's a piece of physics we haven't discovered yet, something that affects both galaxy formation and expansion rate, something that ties together all these discrepancies into a single coherent explanation. We don't know, and that uncertainty is both frustrating and exhilarating. In March 2024, Nature published an editorial titled Cosmology in Crisis. It surveyed leading cosmologists asking whether Lambda-CDM could survive Webb's findings. The responses were mixed. Some argued that the model just needs refinement, better input parameters, more sophisticated simulations. Others suggested it might be time to consider alternatives, modified gravity, warm dark matter variations on dark energy. Professor Adam Rees, a Nobel laureate who helped discover dark energy, told Quantum magazine in February 2024, "This is the most exciting time in cosmology since the 1990s. We're being forced to rethink assumptions we've held for decades. And that's where we are. Not at the end of cosmology, but at a turning point. The discoveries Webb is making aren't just filling in details. They're challenging the framework. They're showing us a universe that formed faster, brighter, more chaotically than our models predicted. A universe where galaxies grew up quickly, where black holes appeared too soon, where structure emerged seemingly overnight. It's not that Lambda-CDM is wrong. It's that it's incomplete. The model works at large scales over long timescales. But zoom in to the first few 100 million years, compress the timeline, look at the details, and the cracks appear. The universe was doing something in those early moments that we don't fully understand. Maybe it's the behavior of dark matter in extreme conditions. Maybe it's the physics of gas cooling and star formation in dense primordial environments. Maybe it's feedback mechanisms we haven't accounted for, or initial conditions that were more varied than we thought. Maybe it's something entirely unexpected, a process or particle or force that only mattered in the early universe and has since become irrelevant. The beauty of science is that uncertainty drives progress. When models match observations perfectly, there's no reason to dig deeper. When they don't match, when the universe hands you data that doesn't fit, you're forced to ask better questions. Webb is giving us those questions. And over the next decade, as more observations come in, as simulations improve, as theorists explore new possibilities, we'll start finding answers. But here's the thing, finding answers will almost certainly lead to more questions. Because the universe has a way of being more complex, more interesting, more strange than we imagine. Every time we think we've figured it out, we build a better telescope, look deeper, and find something that makes us reconsider everything. 20 years ago, dark energy was the big surprise, discovering that the universe's expansion is accelerating, driven by some unknown force. 10 years ago, it was gravitational waves detecting ripples in space-time from colliding black holes, opening a new way of observing the cosmos. Now it's Webb showing us galaxies that shouldn't exist, structures that form too fast, a universe that refuses to follow the script we wrote for it. And that's the wonder of it. We're not just learning facts. We're watching our understanding evolve. We're seeing, in real time, how science works, how observations challenge theories, how theories adapt or get replaced, how each new discovery reshapes the map we're drawing of reality. The James Webb Space Telescope hasn't broken cosmology. It's broken our complacency. It's reminded us that the universe is still full of mysteries, still capable of surprising us, still far more complex than we give it credit for. And somewhere out there, at the very edge of what Webb can see, are galaxies even older, even stranger, waiting to be found. Galaxies from the first 100 million years, maybe even the first 50 million years, when the universe was barely beginning to light up, when the first stars ignited, when the first black holes formed, when chemistry started, when structure began to emerge from chaos. Those galaxies are out there. Webb can almost see them. Almost. And when we finally do, when we push that last bit further, when we capture light from the true cosmic dawn, when we see the universe in its infancy, raw and newborn and nothing like we expected, the story will begin again. Because this is what discovery looks like. Not the end of questions, but the beginning of better ones. Not certainty, but clarity. Not solving the universe, but understanding it a little more deeply, a little more honestly, with a little more humility about how much we still have to learn. The telescope folded like origami, launched on a December morning, unfolded 1,000,000 kilometers from Earth and opened an eye on the early universe. What it saw has changed everything. And what it will see next, what's waiting just beyond the edge of what we can detect, might change everything again. That's the universe we live in. Vast, strange, relentlessly surprising. And we've only just started looking.